Hi everybody, this is the last lecture in reinforced concrete design course that we teach here at IPFW. The final product is a project it's a team project. 3 to 4 students are required to design a 12-story building with the following information. The dimensions of the building center to center are 150 foot by 100 foot. The first floor columns are 15 feet high, the rest are 12 foot high. The columns and beams will be made of reinforced concrete, of course. The concrete will be 4,000 psi, the steel will be grade 60. The dead load will be the self-weight of the structure plus 25 psf, pound per square foot, and the live load will be 100 psf on the stories 1 to 6, and 50 psf on stories 7 to 12. The columns are hinged at the ground level, the foundation level, so it's bent there. The beams and columns must be designed for gravity load only. For the lateral load, if it's wind loading or something, we're going to use shear walls. In this case, that's a common lateral load system in reinforced concrete structure. The floor beams will be spaced at 10 foot. We have to use girders along all the column center lines. The slab will be a solid slab, and it has to be modeled as a shell element, not a plate. And that's basically all the most important given information. I asked them to have like to use square columns for all the corner and perimeter columns, and to use circular columns for all internal columns. The scoring for this project will be, there will be a report, and there will be a presentation, and student evaluation. There will be 7 marks for the presentation coming from the other 2 group members. So the group will give a score for each member of their group, and I will take the average for that. There will be an oral questions or presentation. This is what we are doing now. Each team will present their work, and that will be 7 out of 20. And 6 marks will be based on the quality of the report. So a total of 20 out of 100, 6 for the report, 7 for the presentation, and 7 for students' evaluation to the group members. And we are using ETABS in the analysis and design. And the report will include typically the following: at least pictures captured from the software showing grid lines, dimensions, loading, support, etc. 3D views of the structure, just to show all the dimensions and the angles of the structure. Deformed shape for verification. Analysis results, the action, shear, moment, axial, force diagram. Final design details generated from the software. Stress strength ratios for each member, showing that the member passed the code requirement. Verification of the result through hand calculation. The students must verify their results. And all of the analysis and design must be according to the ACI 318-14. All of the analysis must be according to the ACI code, and again we are using ETABS. And with that, I'm going to give the floor to the first group to present their senior design work. Sorry, design course project work.
Good afternoon, everyone. Today we're going to talk to you about the design of the 12-story reinforced concrete building. My name is Josh Echelin. This is Austin Eichman, Paul Robinson, and Brandon Tucker. In this presentation, we're going to discuss the general design of the building and the parameters given, the design and analysis of the beams, the design and analysis of the square and circular columns, the beam and column placement, the slab design, the analysis of the entire structure, and the final design of the structure. Information that was given for this project was that it was to be a 12-story building. The height of the floors were also given. It was 15 feet for the first floor and 12 feet for the remaining floors. We were given the dead and live loads. There was no wind load on this project, on this building. The material properties, we used 4,000 psi concrete and grade 60 steel for the reinforcement. And we were also given some requirements for the beams, columns, and the slabs.
All right, so I'll start with the beams here. First of all, we took from just the general taskbar and software, we went to this menu for the beams, and we did this later for the columns. There's just one individual beam type, and we did every foreseeable combination that we could think of. So this one, for example, shows a depth of 14 and a width of 8. And we went through and we did every combination that we thought would possibly be assigned by the software. And Austin's going to discuss that later. And as for the requirements for the beam, we had to use continuous beams, we had to use girders along the column center lines, and we used 10-foot spacing. Here, off to the side, you can see the property modifier tabs. We use default for that. And then we have the reinforcement where you can modify. We had them design, and this is where they designed the row, which is that is the percentage of the steel in respect to the gross cross-section area altogether. Next, we have square columns, and like the beams, we went through and we did every combination we could imagine. This one had a lot less because the depth is equal to the width. So this one is a 12-inch square. All columns, both square and circles, are hinged at the ground level. We use square columns for corner columns and perimeter columns. For the circular columns, again, we used every diameter that we thought the software might assign, and all columns, the circles, like I just said, circles and square columns were hinged at the ground level, and we used circular columns for the interior columns.
Next, we moved into the drawing of the actual building itself. And in order to do this, we took the beams that we made, the columns that we made, both square and circular, and we put each of these into respective auto-select lists. And then we drew each on the grid line that we assigned. That way, the software would select it from the respective auto-select lists. So for beams, it would select from the beams auto-select list. For the round columns, it would select from the round columns auto-select list, and for the square columns auto-select list. We placed the beams 10-foot spacing apart, and then they were 20-foot long. And the short direction of the building had the 10-foot spacing of the beams, and the long direction had the 20-foot spacing of the beams. Next, we did the slab design. And so the slab design was modeled as a shell element, and it was important that we assigned also all the floors as a rigid diaphragm. That way the deformed shape worked correctly. The slab thickness was determined to be 6 inches, and that was for a one-end continuous slab, which is L over 28, and our L was 10 feet. Next one, please. Then we assigned the dead and the live load to each floor, and we assigned them as shell elements. The dead load was 20 pounds per square feet on each level, plus the self-weight. The software accounted for the self-weight for us, so all we had to do for the dead load was to apply 20 pounds per square feet on each level. The live load was 100 pounds per square feet from floors 1 through 6, and then 50 pounds per square feet on levels 7 through 12. You can see right here in this dialog box, this is actually a check that our loading was done correctly, and you can see that the uniform dead load was 20 pounds per square feet, and the uniform live load was 100 pounds per square feet. And note that this is actually on story 6, so that's what we wanted to see. Then we ran the analysis, and from the analysis we got the deformed shape. And the deformed shape shows us nice one-way slab action, so we know that everything was assigned correctly. We had all continuous beams and one-way slabs.
Okay, so what we're going to do is look at the shear diagram for a moment here. We have shear and moment diagrams. But what we see here is we see one face of the building. And one of the important things to look for here is that you look for even uniformity amongst each piece of the members. This is a good way to tell that when you're building it, that everything you've clicked is snapped to the automatic points, so that you know that your girders and your floor beams all line up at the exact same spot, that there's no actually missed edges. Originally, when you do this, you may have different diagrams, and that's because we set things as pin instead of continuous, etc. So going through this allowed us to look at every face and then every side view in a plane view and see that all of the beams were given the exact same loading, which showed the uniformity of what we were trying to achieve. This is the moment diagram, and it's the same sort of thing. Now in these moment diagrams, these are rigidly connected. So what you have is you have a strong negative moment at the actual connections, and then it sweeps down into a positive moment and then goes back to the next connection. Again, we have the entire building shown here, and what we want to do is we want to look at each face in each direction and make sure that the moment diagram is uniform and it looks exactly the same for everyone. That way we know how to design. If you look at the dialog box here, we've got the shear and moment diagrams drawn up, and it gives you the actual values. I'm sorry that's a little blurry to see, but it gives you the actual values. And that's what we used when we did our hand calculations, so that we could ensure that what we had was exactly what we designed, lined up with what our paper calculations said we should have had.
So this is the dead load or live load case.
This is both. This is the analysis. After the analysis, we run on to the design. And when we do the designs, it actually selects members for us. And the members are listed here, looking at one point. The entire building is shown on the right. What you end up having with this is when we first designed it, it wanted to change the size of the columns every floor. And doing that is actually the best way to do it from a material savings property. But from a buildability aspect, it's actually very inefficient because you have to change and move your forms at every junction. So the way we ended up doing it was every 4 floors, they stay the same size, and then they change. And the software then built in, it changes the row. It changes the steel reinforcement ratio along the column so that we can make sure that we have a maximum buildability and balance it with the strength. In conclusion, the building ended up being stable. We had a few mistakes originally that we caught in our analysis using the methods described. We were able to fix them. And we used hand calculations that we're going to submit in our report, and they confirmed that there were no major mistakes made. Everything was within tolerance. Here's our finished building showing our deformed shape, and I hope you enjoyed. Thank you.
Any questions?
Were there supposed to be questions?
Yep.
We should have questions.
Students, any questions?
Are you positive that was dead and live load?
I'm not positive. I'd have to go back and look, but it was after the
I
analysis.
think it was.
How you verified your analysis? Because usually when you have a self weight, it's hard to verify for the magnified code. I told you that when you verify something, you verify based on the live load. Because I can tell you what's the live load, right? We have 100 PSRs, right? And the floor beam will have, with a tributary area or a tributary width of 10 foot, right? So for the live load by itself, it will be 100 times 10. It will be 1,000 pounds per foot. It will be 1 kip per foot. What's the length of the floor beam?
20.
20. So the moment will be, for the live load case, WL square over 8. So 1 times 20 square over 8. So 400 over 8, which is 50. That's 50 kip foot. So if your moment for the live load case shows 50 kip foot, that's a verification. Likewise, you can come to any column in here. You see what's the tributary area for the column, and you calculate how much coming to each column from the live load, because it's exact analysis. So once you verify it for the live load, you verify it for the rest. That's how you do the verification, because the self-weight multiplier, you cannot tell exactly how much the self-weight. You can still do it, but you cannot tell. I did not see a sheet with the hand calculation and verification. I did not see
we
that.
just put it in the report.
We just 150,000.
So verified good with you guys?
Yeah, we didn't know the exact stuff, but yeah, we did the crude, weighted concrete or something.
Okay. It looks to me you had the continuous thing nicely somewhere in here, but kind of, I'm not sure you have this fixed here or what?
It shouldn't be. No, it should be in the edges. Yeah.
Okay, which is, usually this is pin, and it's just continuous. That looks fine. So can you elaborate on when you say the auto-select section? So there is 2 options. It's either you create all the sections and you ask him
To design the steel, which is
basically the section.
Yes.
Did you, so that is, the steel need to be designed, not to be verified.
right. For the steel, we did design only, and then after the design was run, we were able to see the actual steel ratios because it picked those.
So you define the section with the steel, with a given row, or you,
No,
each
we
section
defined
is
the
defined.
section.
We told the software to design the
Steel need to be designed,
Yeah,
not to
yeah,
be
yeah.
verified.
Yes.
Or in terms of the dimension.
And did you check the rows, ratios?
Yes. Yes.
And all of that is according to the ACI 14, which is within the software.
Although I thought it was ACI 11 in the software.
There is 14, right, in the last one?
18, 14.
It is? Okay, I believe you.
As long as you select it.
Okay. There is 11, but you can select the 14 and send it. Any other question from other students? One question from one student before we move. It's a must.
Okay, so
Yeah?
can you go back to the shear diagram?
Sure.
Why do you have, I don't know if I'm seeing correct, why do you have that, like, step?
Why does it look like staircases?
Yeah.
Yeah, we had a lot of discussion about that. Do you know Dr. Alhassan?
That's not a staircase actually.
No, but that look, like,
That's the shear you have in the beam is correct.
yeah.
That's the shear in the column, which confused me a little bit.
Okay.
This is the shear in the beam.
Right.
Perfect. But you having a shear in the column, what? I need to see what's your
I
model.
understand
No, but
that.
she's asking, why is this not a straight, smooth line?
Oh, that's
Why is
typical. That's typical how the software
it- The
defines.
software
Yeah,
just
you can-
rounds it off.
Yeah, but that's just typical in there. Unless you define the.
No, that's just the resolution of the image.
It's just the resolution of the drawing, because we couldn't
But
understand why.
I just can't. I need to see your results, guys, because this is too much shear in the column.
Okay.
There should be something in there. I don't know. Did you
Notice
have
it's
it
more
more?
at the top than it is at the bottom.
Did you have like continuous?
Might be the
If you
way.
notice,
Everything was drawn.
this side has a lot more shear than the other side, it looks like in there on the
If
picture.
you have something like that, there's a letter.
It's a wind.
It looks like there's wind being blown.
Did you define one?
No, we don't know.
So I need to verify your model. But there is a question mark about, you will never expect some big shear in the columns. You should expect a little bit from the deflection somehow, which is under gravity load you have symmetric structure. But what's happening here, I don't know. I don't know. I have to take a, I can't explain, but, okay, so good job guys. So send me the report by Friday. Let's take the second group.
Good evening, everybody. This is our reinforced concrete project. I'm presenting today the Jessica Mason, Laura Loretto, Ryan Allred, and myself, Andy Tran. And for the outline, we'll be talking about the project statement, design process, detailed design, results, and we'll be ending with conclusion and questions. The project statement, we have a 12-story building with dimensions of 150 foot by 100 foot. And the materials that we use will be 4 KSI reinforced concrete and 60 KSI steel. And for the columns, the interior columns we use as circular columns, and for the exterior columns we use as rectangular columns. And for the given dead loads, we're 20 PSF plus the soft-frame concrete. And for live loads, 100 PSF for storage 1 through 6, and 50 PSF for storage 7 to 12. For the design process, we had to create a new model, which consists of a new grid, define the materials, as mentioned before, steel will be used as 60 KSI, and concrete 4 KSI. And for frame sections, we had to choose sections for beam and girder, interior and exterior columns. And next, we had to do drawings of the beams, 4 beams, columns, slabs. Next, we had to do the signing of loads. With that, we had to analyze our structure, which can help us design our members, and which will yield our reinforcement required. And here's our grid layout. On the longer side, 150 foot, and it has 5 spans of 30 foot. And on the shorter side, right here, it's 100 foot long with spans of 20 foot, and has 5 spans. And as you can see, these are placement of girders, 4 beams, and beams. And then the circular columns in the interior, and the rectangular columns on the exterior.
For the detailed design, we first, since we don't have the same tools that we have for steel that we could create the AutoSet at least, this time we have to define the cross-section areas. So instead of putting like many of them, we first try to come up with some cross-section areas that could be more suitable for our goal in the project. So we did first hand calculations, and for example, for the circular column, we came up with a model with a cross-section of 27 inches. So we create, for example, circular columns from 21 to 28 inches, for example. And then we did the same for rectangular columns.
So this, where you get this, go back. So this detailing is wrong for the stellar. This spiral reinforced, the circular column. That has to be continuous spiral over there.
Yeah, it is, it's just.
Is it like, where you get this, did you draw this?
Yeah, okay.
Full circle, okay? The spiral is continuous, it's not stopped at all. Go all the way.
Below here, so it keeps going, but it's
Just like
further
it
it's
goes
behind
like-
it.
yes.
so it-
So this is okay.
Yeah, it's, this is, like,
You start with a ring at the top, full ring at the top, then you keep that.
but if it's connected, then it looks like it's connected, so. It doesn't matter.
Okay.
That's why I disconnected.
And then also for the slab, we came up with the thickness and to calculate the self-weight, and then we can avoid. We consider the slab to be fixed support here, and also here is only the half of the span.
So consider fixed at the end?
No, this one is one input is this one. For the girders and beams, we consider two fixed support.
Yeah, because it's obvious, the reinforcement says this is not fixed.
So and then here is one example of our main reinforcement, and then also the temperature shrinkage, and also for the bottom, and here's magnetic moment. Here is an example for the floor beams that I designed the steel for this example as well. And then for the girder,
Here we have the stress that's located in the floors and the beams throughout the entire building. Down here at the bottom, you can see the violet area, or blue area, is going to be the least stress, or the highest stress, while the violet is the lowest stress.
So this is moment?
It's the stress in the building with regards to the deflection. So, as you can see here, you would expect the highest stress to be down here in the middle. Here we have the shear moment diagrams, and the max moment that was found in the building was to be a negative 140 kip foot, while on the shear was 40. And as said earlier, it's expected to be in this type of motion, and then here as well as you're going to, for continuous.
So go back. Don't hide that. This is a good one. So you see this shear, guys? That's a correct shear diagram. That common sense.
That's what you expect.
Yes. Although I will verify what's on the sides, but that's could be because of the building will deflect a little bit to the side. So whenever you see the compression on the left is tension on the right hand side columns, but also need to be verified.
Here we have the location, which is located in the middle of the building, and this is where the highest reactions were found, all the way up to approximately 15 to 1600 kips.
So, like Laura said, we went through and we made a bunch of different sections as their options to choose from. So as you can see for the exterior columns, which were the rectangular, there were many different columns that were used. The lowest, like the smallest column being a 10 by 12 and the largest being 16 by 16. The most frequent column throughout the entire structure was 11 by 16. For the interior columns, those were all the circular columns, with the lowest and the most used being a 24-inch and the largest being a 28-inch. For the beams and girders, you can see the lowest was a 10 by 16, the most used was a 18 by 20, and the largest was a 20 by 22. So that was kind of really what we were getting at for designing the entire structure. So here's the extruded columns and beams and slabs for the entire building. And on the right, you can see that was after we ran the analysis to see what kind of columns need to be used. They're all pink, which in the software means that they're kind of the most economical to be used without failing. So, any questions?
Did you try to generate any of the joints and reinforcement details from the software? Does the software give you any of these reinforcement details?
Yes.
It
You
does?
can go to the report.
Yeah, it doesn't actually draw the detail, but it
Oh,
gives you like specs.
Just give you the
No drawings.
amount
No
that
drawings.
is required.
Go back to the 2 slides. Yeah, wait now. Look at the beams girders on the right hand side. Any question, guys? So you selected 18 by 20?
Why isn't there like 12 by 16 or any of those? Or was it an option and it just
We-
never got chosen?
It
We
was-
created, but it was
It
not.
was an option, but they never
Yeah.
used it. Uh-huh.
These
Are
are
you,
just the ones that
Paul, are you happy with the 18 by 20 or 20 by 22? Did they say something about the ratio between B and H?
Should be about twice the width.
Don't we like to have, I mean,
They are like square.
to have it like H to 1, H to B, around 2, between 1.5 to 2. Why you have big B and shallow D, shallow H?
We actually designed it to where it had all of them, and it just wouldn't let us actually, like, it
You
wouldn't.
shouldn't even define that from the beginning. I won't give a section an option 18 by 20.
Originally, we didn't have those, and
You
it
only
kept
need
failing.
calculations based on 12 by 16, the property they just had to redo all the head count.
Yeah, it kept failing.
That's absolutely fine. Then I will go 14 by 22 or something.
Okay.
I mean, a girder section typically. This is, you can justify this. You can answer me by one thing if you want to answer. You can tell me that we don't want to exceed 2 feet. So we don't exceed the clearance limitation. So we had to go with the maximum 22 or 24. That would be, I thought this is the reason. If there is no limitation on the depth, your B is useless. It's not doing anything to the strength. Okay? But if you have if you intended that not to have a clearance, I mean to maintain the clearance, not to have a section that's over 2 feet depth, then that's how we do it. Okay. One more question from the audience.
I had a question. When you were showing the slab coming in and out, I noticed you had like number 3. Yeah, this one. You've got 4 number 9s and 4 number 9s, but you actually have much greater moment at the positive side than the negative side. Could you have gotten away with less steel on the bottom?
Yes, you can.
I want to elaborate on this one.
Okay.
So this is pin. It is a pin. This detailing cannot give you any fixation. This will not give you any fixation. If you want to have this negative, this reinforcement must be hooked to develop a fixation in here. This detailing will give you a pin. And anyway, you don't need this, by the way.
Yeah.
You don't need this one. If you provide this one, it will give you a slight fixation, but not like that. With some hook so that you create some kind of fixation in here. And anyway, so, by the way, there is one thing maybe I did not cover in the handouts. 4949. If you want some guys, there is a common practice. It's called hard. They hard this one. So you just come, no longer need this reinforcement here. The moment change to positive, you can just on a 45-degree angle bring it up and use it in here. And there is usually for that practice you need to have a hold down force. There is just a slight thing we put it in here to hold it down. That's a common practice. The cutting is more practical, and to me it's safe. You don't have to do this arm reinforcement. But when you have something like that, this is a recommendation to go 6-inch, right?
That's why you just want to show that it goes 6 inches.
But this will not give you
It's not
any
like
fixation.
accurate.
This will not give you any fixation this way. If you want to create some kind of fixation, this reinforcement must be anchored so that it gives you a Fy in here. This must be greater than the, if you want to have a negative moment in here, right? So that means your reinforcement here must give you a Fy, right? So this must be greater than the development length.
So the floor beams are not both,
At both ends?
yes.
No, just pin sitting in there.
Beam?
Yeah, pin or roller sitting there. Continuation over the center one. You will have a negative moment in the middle. So 0, negative. Remember? There is like in the 0, positive, negatives. Positive, negative. Okay.
So
But
you
this-
have a moment at the beginning, right?
No, unless you fix it.
So why did you get that moment at the beginning then?
Because where?
Because you
Because you assign it as a fix in your modeling.
yes.
Your detailing doesn't show a fix.
Okay.
You can ask the software to do anything you want. This is the dangerous thing. I mean, you design it as a fix. Your guy detail it as a pin. You go with the cracking. So if you design it as a fix, you want to make sure your reinforcement provide fixation.
Okay.
Again, let me explain. The development length says this guy, if it's a negative moment, when you did the analysis, must give you a Fy in here, right? So this side and this side must be enough to develop a Fy in here. This will not develop anything. You need to hook it, either this way or that way, to provide a Fy in here from both sides. Okay, good job, guys. Okay, go ahead.
All right, welcome to our reinforced concrete design. This is our building project. Group members are Vincent, Spencer, and myself, Todd. We're going to look at the details of our project, the project description, our grid lines layout, our plan layout, our member design, the area of steel, our deformations, our shared moment diagrams. Our project description, as everybody else has stated, we have our exterior dimensions of our building of 150 feet by 100 feet. Our first floor height of 15 feet, and every additional floor up is 12 feet. We were required to use square columns at the corners and around the perimeter, and circular columns on the interior. All columns are hinged at the ground, and the beams are continuous. We are to analyze the building for gravity loads. Our dead load is calculated as the self-weight of the beams plus 20 pounds per square foot. Our live loads is set at 100 pounds per square foot on floors 1 through 6 and 50 pounds per square feet on floors 7 through 12. It's a solid slab.
This is with the music. We have the music or?
We're trying. Girders along the column center lines, 10-foot floor beam spacing, and our concrete is 4,000 PSI with grade 60 steel.
As you can see, here's our grid layout. We had 30 feet by 20 feet for our columns, as well as 15 feet on the ground floor and 12 foot going up to the next floors. And right here you can see a top view. We have our square columns around the exterior, as well as circular columns in the center. We have our beams located separately by 10 foot.
Which way is your girders? See the columns on the top edge and the bottom edge? They are oriented wrong. Usually we orient them along the walls. So you see these columns? The orientation of the column?
Square columns.
They're square. How does it matter? Is it square? Does it look square to me?
Yeah, it's square. I think it's just the angle that you're at.
Okay. I thought it's rectangle.
Right here we have our designs. We have our 27-inch circular column with a spirally reinforced. We used 1/8 inch spiral at 2 1/4 inch pitch. We had a reinforcement by 12 number 9 bars. For our square corner column, we used 8 number 6 bars. Strips number 3 at 12-inch spacing, as well as our square columns that are not in the corner.
You mean 3/8 spiral, right?
Yes. And for our square columns, we used 6 number 10 bars, and we had a 5-inch slab with 12 number 9 bars for reinforcement. Here we were able to put in our steel areas for all of our columns as well as our beams. It's a little bit hard to describe this image with all of them overlaying it at once, but you can see our building is very feasible, and the amount of steel worked for all the structures.
Once we got everything set up in the model, we ran the analysis and got this deformed structure. And the shapes that we're looking at, it looks like we are getting what we want. The bending appears to be in the right way. Our max deflection, based on just the live load alone, was 0.66 inches. We were allowed 1.0, which is the longest span, 360 inches, 30 feet, over 360, 1 inch. So we were good on deflection. Here's a moment diagram that we got for one of the elevation views. We see, it's a little bit crazy. We see something isn't right with the support right here. We have our moment jumping all over the place. But something that we do notice is where the loading increases from, the live load increases from 50 to 100, we see our moments go up. We expected that. And we see as we go down, the sections get closer and closer together. And we attributed this to our column size increasing as we go down further in the building. Our shear diagram, we see a similar trend. We have the steps going on that the other group had. But again, what we expected on the shear. In conclusion, we showed you how we laid out our grid lines, the dimensions of the project. We got to look at our extruded members. If you look really close, you can see the changing size of the columns. You can see that the outside columns are square and the inside are circles. Our deformed shape, fast deflection. Our areas of steel increased as we went down, as we expected. And our shear and moment diagrams had a couple issues, but the general trends were what we were looking for. Any questions?
I don't have a question, but I have a statement that might help you guys figure out your issue. You guys are designing your beams as columns, and that's why you're actually getting your stress to show in pink on there. And so if you go back and you define your sections, you need to make sure that you change it to a beam design and not a column design.
There is an issue with Gerard even with that project is you have to have them as a column, right?
If you want to, might happen that if you design as beams, like it doesn't allow you to put shear reinforcement. So like at least for me, I had wind loading. So when I was like for my parking garage in the senior design, so then like I had some members failing, and then all the for gravity load it was fine, but then for shear load it was failing, and then I was trying to like, well, I mean the problem is not allowing me to design these beams and put shear reinforcement, so I define them as horizontal columns pretty much, and by doing columns, since it allows it to do the spacing for the spiral or for the stirrups, then I used that as the stirrups for the shear, and that's how like I allow the model.
So either you do what Ryan is saying, but that will give you only flexural design, and the shear design is done by hand, manual, and you show that in your detailing. Or if you want the software to verify the shear design or do the shear design for you, you have to go with the column for the cross section. And again, everything can be like a beam column, it depends on the reinforcement. Now, again, guys, every time you do this in any presentation, this is not a conclusion actually. This is just final product. Call it final product. If you want to conclude, you can. This is not a conclusion. This is basically the final product results, right? So in anything, just have it final product. It's not. What is the conclusion?
What is the conclusion?
The conclusion is that what you concluded. This software is powerful in analyzing that thing, saving a tremendous amount of time. This is the conclusion. You conclude something. You conclude that this software is not adequately designing or the column when you have that. That's a conclusion. Okay. But what is the conclusion? Nothing. You can say now if you want conclusions, you can say that. Then you throw a grid line. So what's about it? So you wanna concluding grid line. So what is it? You can say something about it. You can say conclusion about deformed shape. What is it? You don't have to write it in here, but you can say I want to conclude about that and that and that and that. But this is the final product. You don't have to have a conclusion unless there is something you conclude. Go back to tell you what happened in that thing, in that moment diagram. Here, who can answer? See, it looks like you guys were fine in here. Then you start doing something wrong in here. This is good up to here. Then you start getting something wrong in here. You know what they are doing? They are pinned at this end. This beam is pinned at this end, so it doesn't develop anymore. Okay? So those are, if you go to the assignment, end releases, you will see there is a pin in there, missed in there. So you need to make sure it's continuous all the way like what you had in here. Okay?
So it's actually continuous, not pin, right?
Should be continuous.
Okay,
The
so
beam is continuous.
It should be pin at the end.
Continuous on the mid over to the outside.
You're like, so we were right over.
No, you're still missing this concept. It's easy concept. This is a roller. It means it's not two segments. The beam is sitting on the support. Okay, so continuous over this. How is it going to be continuous over there unless you overhang it? In your case, you fix this. If you fix it, you develop a moment. If it's pin or roller at the end one, no moment. But if there is an internal roller, there is a negative moment. If this is negative. Or like that, like what I told you. See? So it's continuous over this column. Here, either pin or fix. If you want to fix it, you have to provide adequate reinforcement for that. You don't have to. Okay? You don't have to. Any question from the students? Any question? Okay, thank you guys.
Hello, today we're going to present our reinforced concrete project. This is Anwar, Glenn, and I'm Andrew. The project statement was a 12-story building with the first floor being 15 feet high and the rest being 12. We had a dead load on the first 6 floors of 100 pounds per square inch. And then on the 7 through 12, we had 50. The exterior columns were rectangles. The interior columns were circles. And the program we used was ETABS, which is a part of SAP 2000. To start ETABS, you have to click a new model and then define the grid lines. Find the material properties, which was given in the problem statement, then draw the building, and do the testing, and then run the analysis over until you get the correct beams you needed. We designed 20 different columns and 20 different beams.
All right, for the detailed building design, we have a rectangular exterior columns and 10 feet floor beam spacing and 4,000 PSI concrete, grade 60 steel, and for the stairs, longitudinal rebars. Here is our overview of the beams, girders, columns, and E-tabs. We have our 12 stories and stories 1 to 600 PSI for the dead load and 7 to 12, as Andrew said earlier. Here we have the deflection in our beams. After the loads have been applied in the program E-tabs, then we have a typical moment of 12 in the first 5 floors. The typical beam is continuous doubly reinforced concrete beam, statically indeterminate, multi-span, and hinge support, and the developed reaction on the axis beam.
All right, for beam selection, E-tabs, out of the 20 beams that we made for it, selected 10 by 10s, 10 by 12, 10 by 14, 12 by 12, and 16 by 16 beams. For E-tabs, the deciding factor is the reinforcement concrete beam. It's to reinforce areas in concrete that areas weaken tension. Also consider the internal forces acting on the beam and locate the tension zone. For the outside column selection, which are the square columns, they chose 10 by 10, 10 by 12, 10 by 14, 12 by 14, 16 by 16. Square columns are used for the corner columns and the perimeter columns. The columns are hinged at the ground level. Here's the inside column selection, which is the circular columns. And you can see the section it chose, the element type, number of pieces, total length, and total width. This is the table straight for E-tabs. And then we did our hand calculations on our column reinforcement just to double check with E-tabs by finding the tributary area. And then using the live and dead load, we found the ultimate factored load. And then we assumed AS equals 0.02 AG, calculate AG to get our dimensions. And then for the outside square columns, we used a strength reduction factor of 0.65 and then 0.75 for the spirally reinforced. And for conclusion, E-tabs is a very powerful, awesome first grade.
No moment diagram, no shear diagram.
Those are in our report.
Those are the most important thing you need to do.
Yeah, we realize that.
Go back to the guys, you guys are missing something here. When you define a beam section, I said you start with the 10 inch, okay? The first section should be with a 10 inch, 10 by 16. You never do 10 by 14. 10 by 16, 10 by 20, 10 by 18, 20, 22, 24. Then you go to the 12, 12 by 18, 12 by 20. But this is a simple concept. H should be greater than D by about 0.5 at least. Then if you have a limitation, like 24, and your sections are not working, you go, okay, let's say 12, 10 by 24, 12 by 24, 16 by 24, 20 by 20, okay? But this is conceptual thing. You don't start with 10, but look at their section. That's a beam section. If you show this to someone, he said, have you taken reinforced concrete design before? That's what they will tell you. Okay. Go back to the... So no one verified the deflection other than fence screw, right? I know that the shape looks nice, oh, looks good. But this is 0.66.
If our slab is 6 inches, we don't have to. We made our slab thick enough that
No, not the slab, sorry, no, not the slab. The deflection in the beam. He verified the live load deflection. The limit is 1 inch, as he said, and he verified 0.66. I know it looks nice, the deformed shape and all that, but have anybody verified that? That's the first thing you do after the reaction. You get the reaction, as I told you. Then you go to the deflection. Once the deflection is good, it means everything else is good usually. Okay. So that's. Okay, any question for them?
I mean, are there any values to this, like values to the top? Notice the bottom barely deflects, but the top deflects a whole bunch.
There was on E-tabs, we just forgot to put it on here.
Okay. What he's saying, what Paul is asking? No, anybody else? Or elaborate?
Maximum negative.
And it's Ram,
Yes.
about to graduate. Paul says the deflection at the top is bigger than the deflection at the bottom. What do you want to tell him? You tell him, what are you talking about? You should tell him, before, so you don't make a big thing. You should tell him, what are you talking about? What deflection are you talking about? Are you talking about the deflection of the beam or the deflection of the column? Right? That's the question first. So if you're talking about the deflection of the beam, they are almost the same, or the bottom one will deflect more because they have more loading. But you tell them, okay, if you are talking about deflection of the columns, that's accumulate, right? Because each floor is stretching, each column of each floor is
Oh, each
stretching.
floor makes it a little more sunken from the next one. Okay.
That's cumulative at the top.
Okay.
Because look at that column. This is the deflection in the column, the axial deflection in this column. From here to here. From here to here. Any other questions? Okay guys, good job.